everyone. Today's lecture, a special lecture, is to honor the contributions of Professor Robert Cess to atmospheric sciences. Professor Cess is now retired from ITPA and SoMAS, and he lives in Connecticut. He is not able to join us today for personal reasons. So Robert Cess was a faculty member in mechanical engineering in this university, and he was trained in radiation transfer in gases. So back in the 1970s, he became interested in calculating radiation transfer in the atmospheres of the Earth and other planets. And he published a number of very influential papers on the greenhouse effect, the energy balances and feedbacks on the Earth and other planets. And his productivity and his personality was such that the mechanical engineering department of this campus became an attractive place to do atmospheric sciences, and several atmospheric scientists joined the mechanical engineering faculty. And as the numbers grew, we eventually formed the Institute for Terrestrial and Planetary Atmospheres, and then moved to this side of the campus where we joined our colleagues in ocean science and became what is now known as the School of Marine and Atmospheric Sciences. So it is accurate to say that Robert Cess founded atmospheric sciences at Stony Brook University. And in recognition of this historical contribution, every year we invite a distinguished atmospheric scientist to come and deliver this special lecture. So today we do indeed have a very distinguished atmospheric scientist with us, Professor John M. Wallace, or Mike Wallace from University of Washington in Seattle. So actually Mike Wallace grew up in Queens, and he attended for his bachelor's degree the Webb Institute of Naval Architecture, which is located in Nassau County, and which is a very selective and high-quality private school that teaches or prepares people in careers in marine engineering. And but after getting his degree, he decided that engineering is not his forte. So he went to MIT and joined the meteorology department for his PhD degree, which he completed, by the way, in 4 years. And upon getting his PhD, he was appointed as a faculty member in the Atmospheric Sciences program in the University of Washington in Seattle, which for those who are not in this field is a premier school in atmospheric sciences in this country. So Professor Wallace is known for his many highly original and ingenious contributions to atmospheric sciences and climate variability. And so some of the concepts that he introduced and which are widely known are the annular modes and their barotropic structure, and the concept of the Arctic oscillation, which is now widely used in long-range forecasting and in climate research. He also introduced the concept of the Pacific decadal oscillation, which governs long or decadal scale changes in the climate of the Earth in so many regions. And he produced several influential papers on the meteorology associated with the Southern Oscillation. And many of his contributions are in statistical methods, in finding coupled patterns in atmospheric fields. And his textbook, which is entitled Atmospheric Science and Introductory Survey, which, by the way, he wrote when he was 37, has been used to train a whole generation of atmospheric scientists, not only in this country, but throughout the world. And so in recognition of his so many contributions, Professor Wallace has achieved a large number of awards, of which I would mention just a few. So he was given the Rossby Award by the American Meteorological Society and the Revell Medal by the AGU. So Mike Wallace is a member of the National Academy of Sciences. He's a fellow of the American Meteorological Society and also of the American Geophysical Union. He is also a fellow of the American Academy of Arts and Sciences, as well as a member of the Russian Academy of Sciences. So, but before I invite him to give his lecture, I would invite our Dean, Professor Minghua Zhang, to present the certificate of appreciation to Professor Michael Wallace.
Congratulations. Yeah, you sit.
Come over here, Steve.
One more.
Thank you.
Okay, thanks.
Great.
Now we are ready for you. So,
Oh, maybe just a little bit, or, yeah, probably in the front. Yeah, that should be fine. Is that okay for you? Yeah. Fine. Well, thank you for that very kind introduction. And I should say, and with respect to Professor Cess, Bob Cess, we first got to know each other back at the time when he started to go into atmospheric sciences. In 1974-5, we both were on sabbatical, and we spent the year at NCAR, and had a lot of time having coffee together, and subsequently served on many advisory committees in later years, and kept in touch. I miss seeing him here this morning. The other thing I should say is that this much of the work I'm going to present, there are two other people, you can probably barely see the names, but Clara Desser, who's at NCAR, and a senior scientist there, and Brian Smoliak, who's the last of my PhD students who finished his, he just defended his thesis 2 weeks ago. So just to motivate the title, if we think back a year ago to March 2012, some referred to in the popular press then as March Madness, or at least in some articles as this unseasonably warm winter month that was so extreme that in many cases it was attributed to a sign of climate change related to global warming. And there were phrases like climate on steroids, somehow grasping at ways of explaining how this extreme month or the mildness of the winter as a whole was a harbinger of things to come. So my talk sort of deals with that problem of to what extent can we expect to be able to recognize the signature of global warming in the real weather and climate that we're going to be experiencing over, well, the time frame for much of what I'll be talking about is the next 50 years or so, over our lifetime, roughly the time of a human lifetime. So in order to frame the discussion, I'd like to think of this little 2x2 matrix here, which is the ways of thinking about the contributions to climate variability. To motivate those, I have a box with some pictures here. You may recognize Bob Cess, who is in the box of largely thermodynamically induced, his work, much of it dealing with radiative transfer, forced climate change, asking the question, how is the climate going to change in response to prescribed or later on forecasted differences in atmospheric composition. I thought I'd show a picture of what it used to look like here in the opposite corner. Interested largely in free climate variability, spontaneous variability, just part of the internal variability of the climate system, and specifically that part of it that is induced by atmospheric dynamics due to changes in atmospheric circulation patterns, things like El Nino, the annular modes, etc. And for many years I thought of these as being the whole matrix, just these two boxes, but in preparing a previous version of this talk, it occurred to me that there really are two other boxes. And here we see Isaac Held sitting in a box here. I think of him in his paper with Brian Soden on the robust responses to climate change. Thinking of directly forced responses to changes in greenhouse gases, but responses that involve the atmospheric circulation, changes in the atmospheric circulation which then become ways of changing the regional and local climate. And finally, to make it complete, the picture of Mojib Latif, who's been one of the proponents of the idea that free variability, phenomena like the Atlantic multidecadal variability, could change climate not only through their effect on the atmospheric circulation, this box, but also if they involve large exchanges of energy between the atmosphere and oceans, they could could contribute to variations in surface air temperature, thermodynamically. So just to give some examples of the things in the four boxes. First, these two contrasting boxes, the radiative response to increasing greenhouse gases, and we can have natural phenomena here too. Solar variations in solar output, episodic volcanic eruptions, all giving us forced thermodynamically induced variability. Here in this corner we can have a number of different patterns and mechanisms, and I've spent a good bit of my career on those. And then in the other boxes, examples of forced dynamically induced variability. The ozone hole related to the increasing intensity of the Southern Hemisphere polar vortex due to the decrease in ozone over the pole. Polar amplification of global warming is an example, because that's associated with largely with circulation changes. In general, this class of robust responses to global warming, the poleward shifting of the storm tracks, the widening of the tropics, and a number of other proposed responses fall in this category. And then examples of free variability of a thermodynamic type. It takes a long time to observe the Atlantic multidecadal variability. This is such a slow process that it's questionable whether we can make a convincing case based on observations that it can heat and cool the Earth. But certainly we can see that in ENSO on a year-to-year basis. ENSO does perturb the global mean surface air temperature by several tenths of a degree, and that's clearly a robust, highly statistically significant signal. So if ENSO can do it, at least it is conceivable that the Atlantic multidecadal variability could do it on much longer time scales. So just putting them all together then, and then talking about this matrix in a little different way, thinking about how we might distinguish among these four categories of variability. How do we know which is which? Well, if we have if we have ensembles of simulations, and especially if we have large ensembles, and I'm going to be showing you some of Clara Desser's results today with ensemble sizes of 40 or so, then in the world of that model, then we can calculate, we can put all the members together and get the ensemble mean changes in surface air temperature, the circulation, and anything we wish to look at. And the ensemble mean, if it's a big, lots of ensemble members, we can reasonably associate with force variability. And then the departure of those same fields in the individual ensemble members from the mean, then we can associate with the free, spontaneous variability in that model. So, given large ensembles, this is a very simple problem to sort out which is which. But of course, given the real world, we have only one ensemble member, and so we're not going to be able to do that in a very simple way. And then to cut things the other way, we can, through various statistical approaches, we can identify the dynamical contribution to changes in climate, largely by regressing changes in surface air temperature on changes in circulation. And so we can make a statistical determination of the dynamically induced variability, and then what's left is, sort of by definition, this residual will be the other boxes, the thermodynamically induced variability. So I'm going to go back and forth here a couple of times in this talk between work of Clara Desser's that's been, it's all been published now, in which she's analyzed a set of 40 integrations with the CCSM3. There's now a later version. She's continuing this work now with the CCSM4. But I'm going to be showing from the model as it existed a year or two ago. And these are all models in which they were started from initial conditions back at the turn of the century. I think there were just the synoptic maps for successive days of the same month or two. And from each set of initial conditions, they were run forward to the year 2060. And then the period of analysis was from 2005 to 2060, the 55-year period. And we're going to be looking at trends from about here, from 2005 to the end of the integration at 2060. Of course, by the time we start looking at 2005, they've lost all memory of the initial conditions. And we'll see that in this set of experiments, the memory of the ocean doesn't really matter much anyway. So that's the experimental setup. And so just to keep the graphics simpler, we'll look just at North America here. And these are the trends from 2005 to 2060 for the winter season. And I'm going to just, for the sake of saving time, just focus on DJF for all her results. And so each of these maps corresponds to an individual ensemble member, one here, and this is the last one, this is 40. And then this is the ensemble mean here at the end. So this is the average of the 40 ensemble members. So you can see that they all have warming, they all have polar amplification. But there's considerable diversity. Some of them will see some blue spots, which are indicative of even a little bit of cooling in that 55-year period. And some will see a lot more red further south than others. We're going to look at some of these in more detail. So here we just take this group and look at them a little more carefully. We see some real diversity among these. And just to keep it simple, I'm going to focus on these two, which are the most diverse. So we've looked at all 40, and we picked the two that differ from each other the most. So you see, for those of us living in Seattle during this period in the model world, there is no global warming anywhere in the Pacific Northwest. There's none for us, anyway. And nowhere in the 48, the lower 48 states, is there really large warming. In contrast, number 22, it's very, very large. Certainly it was surprising, I think, to both Clara and me to see what large variations there are. So we can, if we look at these individual runs, number 4, the cool one, and we look at the ensemble mean, which is the forced part of the signal, that's represented here, and the difference is the part that's presumably due to the free variability, which produced cooling, dynamically induced cooling over the almost all of North America, and a lot over the lower 48 here. We look at the same thing for the contrasting run, the warm run, and you see that there's dynamically induced warming over most of the lower 48. So the difference between these two is entirely attributable to the dynamical component. So then the same runs, this is the, let's see, these are the same 3 maps that we've looked at. And time series here for a couple of selected locations. I'm going to just focus on 1 or 2 of them. The Seattle time series from the model. And here is the Seattle time series in the warm run. And here's the Seattle time series in the cool run, number 4. And you see almost no warming. And then for those same runs, here's the time series for the United States, steady climb, and just a little bit of warming in the cool run. The globe, though, if we average over the whole globe, they're not so different. They both show global warming signal. If we were doing that traditional analysis of the global mean, and this is just land temperature, we would see a robust global warming signal. This is, you won't need to look at this in any detail, but just to show that this kind of experiment has also been done with other models. This is the ECM model, and they've been done in a retrospective as well as a prognostic way. These runs are for the period for the past, for 2070 to 2005, and trying to simulate 20th century climate given the specified distribution of greenhouse gases. And we can see a lot of diversity in these runs as well. So the NCAR model is not, or the CCM is not atypical here. And we can see the same size differences as we go back into the past. In fact, these differences are larger than the others because the averaging period for the trends is shorter. This is a 35-year span, the others were 55 years. So now we'll come back to some more of Clara Desser's work in a few slides, but now I'm going to jump to another paper that I'm going to show some slides from so that we can look at observations as we look at the models. So now we're looking at observations. This is a recent paper with Chung Fu and myself and our graduate students. And so the top curve going from 1900 to present is the global mean surface temperature. This includes both land and ocean. And the solid curve here is the observations. The dashed curve these were the mean of the CMIP-3 simulations. And you can see them tracking very well, although now that this hiatus in the warming in the last 10 years is not caught very well by the simulations. They keep going up. So then, so this is global mean. This is global mean surface temperature. Then GSAT, that's surface air temperature. This is land only, still global. And you see broadly similar distribution, but more rapid rise here during the late 20th century. In fact, something like a factor 2 or so. And then if we look at just the Northern Hemisphere alone, and we look at just boreal winter, which is the season I'm going to emphasize in this talk, then the rise during this period, 1965 to 2000, which is the focus of our paper, is very steep. That this, the Northern Hemisphere high, the Northern Hemisphere winter accounts for a disproportionate fraction of that temperature rise. So then a little more, we look at the 2- and 3-dimensional distribution of the warming. Here the map, surface air temperature, land only, the observations, and a zonal average of those observations here. And this is the, in this case, in our study, it's a 6-month winter season. But this is the cold season, this is the warm season. So the thing that really catches your eye when you look at these together are these big patches of strong warming high on the scale over the high latitude Northern Hemisphere continents. And you see they're largely poleward of 40 degrees. If I put the 40-degree line, kind of cuts across the bottom of them. So if we look at the domain poleward of 40 degrees during the cold season, that's where we've had the really strongest warming. And we don't see anything like that in the warm season. In the warm season, it's much more uniform, sort of, the pattern is kind of amorphous. It doesn't look like anything very recognizable. And we can see this reflected in that rather flat distribution in the zonal average, and these red areas showing up as a real peak here in the cold season. These are the corresponding means of the AR4 simulations, and the these are ensemble means. They're multi-model ensemble means. And so this was an average of, I think it's of order 20 integrations. And so we don't see these big blocks of color. We do see enhanced warming along the fringes of the Arctic, but it's not as strong as in the observations, and it's not in quite the same place either. It's up along the Arctic coast. And we don't see that during summer in the model. And if we were to compare the warm season in the model and the observations, it wouldn't be such a disconnect. But these two really look quite different. This was the focus of our PNAS paper. Just to show the similar results, this is just for the cold season, and this is for the longer period, 1920 to 2008. We chose 1920 because we weren't sure we could trust the data that well before it. And you see it's similar picture where, though not quite the same shapes, but a lot of warming over the high latitude continents during the winter, much less during the summer. In this long period, we start to see these zones where there has been no warming over the southeastern United States and China, which some people believe may be due to aerosol forcing. But these are observations, so if it is aerosol forcing, this is one signal that is actually detectable in our one ensemble member for the observations. So now switching back again to work of Clara Desser and colleagues, and I think a very interesting study in diagnosing where is this diversity coming from in the dynamical contribution. So this is an effort to try to get at the circulation patterns that cause those individual ensemble members to have such diverse surface air temperature trends. So first, an analysis of the sea level pressure field, and this is for, it's not indicated here, but this is for the, oh yes it is, for the months of December, January, February. So the Northern Hemisphere winter. Separate analyses for the Northern and Southern Hemisphere. So these are just spliced together for the sake of convenience in showing them. But think of this as separate analysis from this. So we see the leading EOF of the winter sea level pressure looks like the angular mode with opposite colors in the polar cap and mid-latitudes. The Southern Hemisphere, the same thing. Actually, in the CCSM, we have similar patterns for the other season as well. So that's a very robust pattern. The angular mode is the dominant mode in the sea level pressure field. And it also is the dominant mode in I have to, one very important thing. This is the leading mode in the trends. So this EOF analysis, we think of EOF analysis as normally being done in time, where we take different time samples. In this case, time for every sample is the trend from 2005 to 2060. But the diversity is coming from the fact that it's 40 different ensemble members. So the leading EOF of the trends looks like the angular mode. I should have emphasized that. And we do the same analysis on the CAM3 is the atmospheric component of the same model here, where the ocean is just forced with the climatological mean annual cycle year after year. I think that it has the trend in it, but none of the diversity. So none of the patterns in the CAM3 are entirely atmospheric patterns. They're not due to atmosphere-ocean interaction. And they're virtually identical. Which is a very important result. It says that in these experiments, the atmosphere is doing all the work. The ocean is just going along for the ride. And this diversity in the ensemble members is coming from the diversity of the atmospheric patterns. Now, in those experiments, over the 55 years, if we look at the PDF of the index of this annular mode pattern, we see that the PDF shifts to the right, that there is a tendency towards the high index of the annular mode, towards a lower pressure in the Arctic, higher pressure around the mid-latitudes, stronger subpolar westerlies, which contributes to a warmer high-latitude continent. That's manifested by the shift in the distribution here. But within the individual ensemble members, which determines the width of this distribution, that trend is quite diverse. Not all ensemble members have a positive trend. Most of them do, but these over here have negative trends. Well, I should say that, so they sort of explain a little more carefully. This red, it's the red histogram that is the the model result with the trends. The gray histogram is just for reference. That's from a control run. It shows in the control run we have the diversity of the individual segments of the control run. The trends are quite variable, but the mean trend in the control run is 0. And so that's centered about 0. So in terms of our matrix here, that overall shift towards higher values in this model can be viewed as a robust response, a forced response to the greenhouse gas forcing in it. But the spread of that histogram, the fact that each ensemble member has a different trend, that's a reflection of the spontaneous and internal variability. So just to look at that dynamically induced variability a little bit more specifically what it's related to, here is the cold member. This is the ensemble member which had the least warming over the continental United States. This is what the sea level pressure trend, DJF, looks like during that, in that run. So in that run, the pressure is rising in the North Pacific. It's falling over here. There's more, you might recognize, the synopticians in the room would recognize this as kind of a cold weather pattern for the United States. So it says that the sea level pressure field is trending in that direction. Here sits the counterpart for the warm ensemble member, pressure rising down in here, more marine air coming in across the Rockies and kind of flooding North America with air that was warm to start with, been adiabatically warm going across the Rockies and contributing to this extraordinary warmth. So we can think of the free variability then as being due to the diversity of these sea level pressure trends. So, and then we can actually understand those in a little more detail if we compare this is the same leading EOF of the sea level pressure trends. But now in this one they're represented as contours. So this is the same annular mode pattern with pressure rises in mid-latitudes, falls in high latitudes. And here in this figure, the color is the trend in the surface air temperature. So you see that we have excessive warming in this area of northern Eurasia, where we have the marine air coming in over the cold continent, keeping it warm. We have cold, reduced trends over this area where we have enhanced northeasterly winds over, say, over North Africa during the, if we have in the months the runs with this pressure pattern. You can see that in a little more detail here. So if we have so ensemble members with a tendency towards a sea level pressure pattern that looks like this EOF, then are going to be excessively warm here, excessively cool here, and so on. So just to demonstrate that that indeed does account for the differences in the surface air temperature patterns. This we've seen, and this is what you get if you regress out the variability that can be explained by the first 5, the first 10, the first 20 EOFs of the sea level pressure field. And the point is that as we remove more and more of the dynamically induced variability, these patterns get to look more and more alike, and in the end they should look like the ensemble mean. I'm going to sweep a lot under the rug in this slide because, in fact, just statistically, optimizing the fit to the dynamically induced variability without overfitting is a tricky business that we're still kind of working on here. But I have no doubt that we'll be able to, that we can explain most of this variability with the circulation patterns. So now this is the last switch, and to come back to the observations again. Here, this is just for the cold season. The trends, 1965 to 2000. This is not, however, it's not sea level pressure trends. This is just the surface air temperature trend. This is just what we saw before. And this is the part of it that can be fit or attributed to the dynamical, the trend in the sea level pressure field, which I think if I, yes, in fact, let's come back to this. This is the trend for the same period of record, 1965 to 2000 in the sea level pressure field. This was an unusual period during the 20th century when we had a large trend, in fact, towards the high index of the annular mode. Lower pressure in the Arctic, higher pressure around the fringes here in mid-latitudes, and a large trend in the Southern Hemisphere as well. We know this was due to the ozone depletion from numerical experiments. Not clear whether this change in the Northern Hemisphere was due to sampling variability or whether ozone may have contributed a bit to it. But at any rate, this is what the trend was from observations. And if we use this pattern to take out the dynamically induced variability, this is the surface air temperature variability that we can explain with this pattern. And now we can go back to this previous slide. Here's the raw surface air temperature trend during this period. Here is the dynamical contribution, and here's what's left when we take that out. And so in the process of taking this out, we remove a lot of this color here in the high latitude Northern Hemisphere continents, but not all of it.
So,
Yeah.
That's a question. So for the dynamical contribution, you sort of do the regression
Yes.
based on month-to-month variability?
That's right, and we use the high frequency variability to get the regression coefficient, and then we apply that to the trend. That's been done number of previous studies. So we might ask, well, does this explain this rapid warming, wintertime warming of the Northern Hemisphere? Does it explain why global mean temperature rose so rapidly during this period? Well, this table is an attempt to sort of sort out how important is this. So we have the results for the boreal cold season here, we've been looking at, and here's the other season, just for reference. And so this is all, this is surface air temperature over land only, poleward of 40 degrees. So during this period, in the raw data, at high latitudes, it was an enormous change, 1.72 degrees during this 35 years in the raw data. But if we take out the dynamical contribution, that drops to just over 1 degree. And here's the corresponding trend in the other season. So we knocked this down almost, but not quite, to this. So we removed most of the excess warming by making this dynamical correction. For the rest of the hemisphere, we don't make any dynamical correction in this paper. It was 0.70, and so it's less than the warming at high latitudes, but not that much less than the warming with the dynamical correction. And just about for the rest of the world, south of 40 degrees north, not much difference between the two seasons. So then if we go global, if we just take global land temperature, we put these together. In effect, this is what it is raw. The dynamical adjustment still makes a substantial difference. It lowers that to 0.8. And that 0.8 isn't so different from the other season, 0.72. However, if we add in the ocean, which wasn't warming nearly as fast, that just really dilutes this effect. And now applying the dynamical correction makes only lowers it less than 1/10 of a degree for the globe as a whole. And then if we were to put the two seasons together for a global mean, it would knock this down to about 0.04 of a degree. So if we want to say how important is these effects I've been talking about in terms of global mean temperature averaged over the year, I would have to say it's not very important. But it is very important in explaining why the Northern Hemisphere land temperature warms so rapidly during the cold season. Now, just a further slide to argue that the dynamical adjustment is useful. Here is a time series of, this is Northern Hemisphere land temperature, the raw data. And here is with before and after the dynamical adjustment. The red curves in both are the warm season, the blue curves are the cold season, and they're 6-month seasons. So together they represent the whole year. So you can see that by applying the dynamical adjustment, and which is applied only to the winter data, because that's the season with the big contribution, we make these curves a lot more coherent. We bring them into line so that winter and summer are varying coherently on a long time scale. This is the similar demonstration if we take just the part of the Northern Hemisphere forward of 40 degrees and even more dramatic sort of alignment of these. So I think doing this dynamical adjustment is going to be useful in evaluating models and in interpreting what the models are giving us. So I'm getting very close to wrapping up here. I guess I just want to have a few slides dealing with this box here, asking the question, could the Atlantic multi-decadal variability have a big effect on long time scales? The Mojib-Latif part of the box. And this is, these curves were generated by Zhaohua Wu at Florida State University. The brown here is the observed global mean surface temperature, GST record, land and ocean, from 1850 to present. A lot of year-to-year variability. And then he's done a decomposition of this time series using this method of empirical mode decomposition of Norden 1. And that yields for the gravest mode this red curve, which looks like a very nice sort of nonlinear trend that's suggestive of the kind of very slow climate variability that we've seen. And then if we take the gravest mode plus the next mode, we get this green curve, which captures most of the ups and downs in the trend. In fact, it'll it looks like it will eventually come around here to capture the present hiatus, but it's too stiff to really change that fast. So it looks like this. So if we pose the question, we could argue that the red curve fits the forced variability very well, the greenhouse warming signal. But to what do we attribute the difference between the red and the green curve? Is it forced? Is this the signature of the AMO? Or
Mike is dangling on the cord.
that's what's
Follow the cord. No, follow the cord from what you got in your.
Oh, I see. So is this the signature of the AMO, or does this represent variations in aerosol loading over this time? It's been proposed, for example, that this flattening represents the increase in aerosols following World War II, a lot more pollution, balancing the warming, and then comes the Clean Air Act around 1980, and clean up our act, and we start to lose, starts to catch up again. So that is being hotly debated at this point. I won't say anything more about it, but I think that's one of the real central issues in attribution, is figuring out what these variations are due to. So I guess one of the bottom lines of my talk is that we have, I think, traditionally in climate science had a view of this 2x2 matrix where in terms of the activity, the amount of funding, the amount of human years going into it, the forced thermodynamically induced box, Bob Cess's box, if you will, has been the dominant one. It's what you see mostly in the IPCC reports. And I guess the purpose of my talk is to argue that the other elements are important, and that I think by the time of the next IPCC report, the one 5 years from now, we're going to see a lot more emphasis on this uncertainty in the trends because of the dynamically induced variability. Looks like what do you think in terms of time?
Yes, sir. 5 or 10 minutes more.
I can go to, more like 3. So then this comes back to last March. I guess I'm a real skeptic as to whether we can invoke global warming to explain March Madness. I don't, given the kind of spontaneous variability that the atmosphere is capable of, I don't think that we're going to have any definitive attribution of events like that. So where does that, I come back to this last little fragmentary topic because having said that, you might think that I'm not concerned about global warming, that I'm a skeptic, and I want to convince you that I'm not. And I want to make, and I want to argue that although at our latitudes, the attribution of climate change is very difficult, in the tropics, it's a different story. And the reason it's a different story is that these are observations, land, surface, air, temperature. The reason it's a different story is because the natural variability is so much greater over higher latitudes than it is in the tropics. The tropics, we have this quiet background against which the long-term changes are much more prominent. And the reason that background is, the reason the tropics are so much quieter or largely dynamical has to do with the fact that on a rotating planet, we can have large temperature gradients in the extratropics, and they can be geostrophically balanced. In the tropics, we can't do that. And so if we look at the standard deviation of temperature on short time scales, and this is month-to-month variability, just short range month-to-month variability as an example, we see that it's very quiet in the tropics, in the zonal average here, see, quite small, and then it increases particularly over the Northern Hemisphere where we have these large continents, and gets to be larger by, on average, in an annual average, which is the black, a factor of 4. And in the cold season, it's even like a factor, the ratio of this to this is a factor of 5 or 6. So there's a tremendous difference between the tropics, the extratropical Northern Hemisphere is just so noisy. And I would argue that we, human beings and ecosystems, have adapted themselves to these big changes in variance. Organisms living in the tropics are not used to big temperature variability. And I should say, we see the same kind of curve for the day-to-day variability. You see it for the diurnal cycle even, that the deep tropics are extraordinarily quiet, and life has adapted to that. Whereas we're used to living in a much more noisy world. If we take the inverse of the standard deviation, it's really makes the point quite dramatically. And so because conditions are so quiet in the tropics, if we think in terms of a normalized or standardized rise in global temperatures, actually the rise is bigger in the tropics if we divide it by the natural background variability. And here, demonstration of that, the trends. Let's just look at 1965 to 2000. These are the raw trends, and we see the polar amplification. We see the trend in the cold season is greater than the warm season. But if we standardize grid point by the high frequency variance of the temperature, then it's the tropics that have the big variation. And in fact, large areas of the tropics have had temperature rises on the order of 1 standard deviation. Depends just how you normalize, just what you use for a standard deviation, just how big this is. But it's of order, I would say roughly in the tropics, it's getting to be of order 1. And if you think of what that means in terms of extreme events, if we have, if we define, say, the extreme event as being 2 standard deviations above normal in, say, this normal distribution here, and if this is the cumulative frequency distribution here, 2 standard deviations above normal, it's about 2.5%. And so that's what we get here. And if the distribution slides 1 standard deviation towards warmer, we go from the black curve to the blue curve here, what was the outlier here, 2.5%, becomes 16% or so. And of course, if we go 2 standard deviations, it gets to be 50%. It becomes the norm. So if we're talking in terms of extreme events, for temperature, the tropics are way ahead of mid-latitudes. They've had almost a whole standard deviation of temperature rise. We've had more like half a standard deviation. So we've had a rise, only maybe what was a 2.5% event is maybe a 5% event. Much more difficult to detect. So, and then in a broader sense, I guess I'm concerned not only about climate change, but when we think about the tropics, where we have so much of the world population, the arable land is, they're not making it anymore, and in fact, some of it is going out of production as it's being misused. Serious crises in fresh water, groundwater depletion in India and China. Serious losses of topsoil in many countries, and overall of the globe, the depletion of needed mineral resources. I guess my own personal feeling is, in talking with the press, we ought to be more holistic in our dialogue rather than doing it Al Gore style and making everything pinned on climate change that is going to be hard to convince extratropical people is even happening. So I'll leave it with that.
We have time for a few questions. If you would like to ask a question. Yes, Kawasima?
John, for the free part, when you're calculating the free part, you calculate it by subtracting the force, right?
Yeah.
But that could also be due to the just errors in the model. How do you account?
Well, in this case, we assume that the models are perfect for that purpose. This is just really
it's
a
an
thought
ideal world.
experiment.
Right.
Yeah.
Yes,
Over.
Marvin?
Mike, what about, there's currently an emphasis on climate services, on shorter-term prediction of climate. What are the implications of forced and free on that activity?
I guess it depends, with the free, it depends upon the nature of the free, just what is the forcing agent in the free. Where there is physics, as in the case of ENSO, and quite possibly in the case of the Atlantic multidecadal variability, then there is the potential for prediction on those timescales. But when it is just, when the climate system is behaving as if it's just responding to stochastic forcing, then there really isn't much predictability other than persistence. So it depends, I guess.
Thank you.
Yes. The annular mode robust signal in both CCS and 3 and COM. Well, that suggests that there's the change in the ocean part not so significant or not so important.
In these results, it makes very little difference whether the ocean is allowed to change or not, because you can replicate almost everything with the atmospheric model alone, with the ocean doing nothing. But that doesn't necessarily mean that the real world is that. The atmosphere is so much in control.
So you have any?
Yeah. So in the fourth mode,
the vertical stability would change, and as you mentioned, the westerly jet would change. The expansion of the tropics.
Yeah.
Will that affect the free mode? Presumably,
Of course,
that
yes.
would change.
But the methods, the mechanisms you mentioned, that is what I would call the forced dynamical
Yeah.
part of the variability. And then, of course, there is interaction between the phenomena in these boxes as well, just as there is between the people in the boxes.
So in that case, then the separation becomes difficult, is that right?
Well, you can still, I think formally you can still say that this is spontaneous. It's spontaneous in this changed world. But I think it's still, you can always defend, you should always be able to defend that choice of boxes and the use of the methodology. You might have to qualify it in some ways.
And last question is from Steve Short.
Hi. Yeah, I found your presentation very refreshing, especially the pointing out the wide divergence in these 40 ensemble members. That was astonishing to me, and I think it's very valuable to point out that great divergence in these ensemble members that are starting from just slightly different initial conditions and leading to such a divergent picture. One caution I would like to raise, and you showed in one of your figures the sort of the trend of the CMIP3 ensemble over the 20th century and how well they were sort of in some sense reproducing global mean. But the quantity that you were plotting, and you're not the only one guilty of this, it's commonly done, is temperature anomaly, as opposed to the actual temperatures that come out of the CMIP3 members, which are spread over something like 2.5 degrees. It's a huge spread among those members. The anomalies all give the same trend, but the spread among the members is much larger than the increase over the 20th century.
You know, what you raise, I don't even know what, that question should be asked to Clara Desser, and I don't know exactly what she would say, but maybe they've already.
Well, her model probably has a sensitivity such that that her ensemble members are not subject to this. But if you look at all the members of the CMIP3 ensemble, it's a huge spread.
Right, so they've all been adjusted to get rid of that, and of course that's another source. Yeah, on top of everything else, maybe a fifth box.
Okay, so let us thank Professor Wallace for